Good morning, students. I am Dr.R.SUGANYA, Department of Computer Science with Cybersecurity. Today I am going to talk about edge computing. Introduction, history of edge computing, hardware and software, about open source tools for edge computing, observations, facts, challenges, and military applications. Introduction, edge computing is a distributed computing paradigm that brings computations and data storage closer to the location where it is needed, often at the edge of the network. This contrasts with traditional cloud computing, where data is sent to centralized data centers for processing. The goal is mainly to reduce the latency, to save bandwidth, and also to improve the responsiveness of applications by processing the data locally or near the source of data generation. History of edge computing. The early beginnings, 1990s to early 2000, the content delivery networks, the concept of edge computing can be traced back to the development of CDN, that is Content Delivery Network, in the late 1990s. CDNs were designed to bring the content closer to users by catching the copies of data at strategically located servers, reducing the latency and improving load times for web content. Remote office or branch office solutions. In the early 2000s, companies began deploying localized computing resources at remote offices or branch locations. This allowed these locations to operate independently of central data centers, reducing the need for constant data transmission and improving operational efficiency. Emergence of cloud computing. Cloud computing boom. So in the mid 2000s, the rise of cloud computing, centralized data processing in large data centers. While cloud computing offers scalability and cost efficiency, it has introduced latency issues for applications requiring real-time processing, highlighting the need for a more distributed approach. What is fog computing? Here, the term fog computing was coined by Cisco in 2012 as a concept that extends cloud computing to the edge of the network. Fog computing introduced the idea of processing data closer to where it is generated, laying the groundwork for modern edge computing. Formalization and growth. Internet of Things. The proliferations of IoT devices in 2010s created a massive influx of data, much of which needed to be processed in real time. This led to recognitions that cloud computing alone could not meet the demands of IoT, driving the need for edge computing solutions. Mobile edge computing. The European Telecommunication Standard Institute introduced the concept of mobile edge computing in 2014. Mobile edge computing focused on providing IT and cloud computing capabilities within the radio access network, which is close to mobile users, enabling low latency applications such as augmented reality and autonomous driving. Modern era in 5G and that is to present, that is edge computing will be like a driver for it will be a rollout of 5G network, which has been a significant driver for edge computing. So 5G's low latency, high bandwidth capabilities complement edge computing, enabling new applications such as smart cities, remote surgeries, and immersive gaming experiences. Hybrid cloud and edge architectures. The 2020s have seen the rise of hybrid cloud and edge architectures, where cloud and edge computing are integrated to provide flexible, scalable, and responsive solutions for various applications. Standardization and ecosystem development. Organizations like ETSI, the Open Fog Consortium, and the Linux Foundation's Edge Foundry have been working on standards and frameworks to support the growing edge computing ecosystem. Hardware in edge computing, edge devices, IoT sensors, and actuators. These are often the primary data sources in an edge computing setup, collecting information from the environment or controlling physical systems. Smartphones, wearables, and cameras. It serves as edge devices in various applications, processing data locally before sending it to the cloud or a centralized system. Edge servers, micro data centers, small scale data centers located closer to the edge, providing local processing power and storage. These are typically ruggedized for deployment in remote or harsh environments. Industrial PCs and gateways used in manufacturing and industrial settings, they connect legacy equipment to modern IoT networks and it performs the real-time processing. Network infrastructure, routers and switches. It facilitates communication between edge devices, edge servers and the cloud. 5G, 4G, LTE private network. It provides low latency, high speed communication channel essential for real time application. Specialized hardware, GPUs and TPUs for AI and machine learning tasks at the edge processing large data sets in real time. FPGA or ASICs, custom hardware used for specific high performance tasks such as encryption, video processing or complex mathematical computations. Software in edge computing. This edge operating system, Linux based OS, it is example Ubuntu Core Yocto Edge Foundry, which is often used in edge devices for their flexibility, security features and community support. Real-time operating system, which required for applications where timing is critical such as in industrial control systems, middlewares and frameworks. Edge orchestration platforms, IoT platforms, AI or machine learning frameworks. So security software which has tools, intrusion detection prevention system and device management software. And also we have data management and analytics like edge databases, stream processing engine and virtualization tools. And also we have communication protocol like MQTT, COAP and AMQP, HTTP and REST APIs. And there are some use cases of edge computing like smart cities, healthcare also, and industrial IoT, retail, autonomous vehicles. So there are some open source tools used in edge computing like Edge Orchestrate, EdgeX Foundry, Open Horizon, Beetle, IoT platforms and middleware like Eclipse, where operating systems and middleware which is used like Ubuntu, Yocto for Yocto projects, and it has some reduced latency also. When we observe it, we can see that the latency has been reduced and the bandwidth is also been optimized with reducing cost. So it also enhanced privacy and security, scalability and resilience and reliability. Okay, it also supported for IoT and AI. The energy efficiency is very lower and it is making them suitable for environments and it is very high priority. Challenges in management and deployment. Despite its advantages, edge computing introduces new challenges. There are some facts. It has like a market growth, reduction in latency, IoT devices, 5G synergy, energy efficiency, security, data volume, use cases, autonomous system, hybrid architectures, data localizations, content delivery. And there are some challenges of edge computing like security and privacy, data management and consistency, scalability, interoperability, network reliability. Okay, so why we have to care about this, which have applications like always we have used in today's technology, self-driving cars and industry 4.0. So it's pretty obvious that ingesting data to a distant cloud a realistic operation. So we have seen here like first the mechanism was there and mass production, and the third one was computerized automation, and now the cyber physical system is included. So we can see now how it's been application that can't tolerate this particular latency, so it can be a reason for failure. So 81% increase in revenue of edge computing by 2018. Okay, so 72% the average anticipated annual revenue growth for IoT edge vendors by 2018 end. The edge computing is optimized for cloud to move the compute close to source of data to the edge. So we can see here the edge computing, so how it has been for real-time data processing and for also for big data analysis, and how this sensors and controllers were used. So edge computing characteristics like geographically it is distributed, it is scalable, it's autonomous and distributed, and edge computing is contextual and low latency, and real-time interaction